The data being returned from LRO and the other probes draws a clear image of the evolution of the lunar surface and why it is composed of exactly the same elements as the Earth. After coalescing from the Earth-Theas collision, the proto-moon cooled, then suffered several major collisions from orbital debris, which created many of the largest surface characteristics, including the mares. Cratering continued relentlessly over the millennia, drawing the familiar lunar vista.
My name is Lynn Carter. I'm a research space scientist, and I work with the Planetary Geodynamics group here at Goddard. I study the geology of planetary surfaces, the Earth, Moon, Mars, Venus. There's a lot of things you can learn about the Earth by studying other planets. For example, on the Earth, we have a lot of erosive processes. You know, it rains, it washes parts of the surface away. We have plate tectonics, which recycles the crust. But on other planets, those processes don't necessarily occur. So for example, when we look at the Moon, we're seeing a surface that's much older. We can use impact cratering on the Moon to sort of understand how many impacts happened, the size of the objects that were hitting each other in the early solar system. One of my favorite things is to use radar remote sensing. For example, on Mars, we can use radars to sound all the way to the bottom of Mars polar caps and see all this layering within the polar caps. And on the Moon, we're using it to study impact cratering. Sometimes when an impact crater is formed, a huge sheet of melt is thrown out. This melted rock flows across the surface, but then over time, it's covered over by stuff from other impacts. But with the radar, it just blows right through all of that, and you can see this beautiful image of the melt flow coming out of the crater.
Launched with LRO was LCROSS, or Lunar Crater Observation and Sensing Satellite. It deployed sometime later than LRO and had a finite mission. LCROSS and the rocket stage that delivered it were deliberately crashed into the craters of the South Pole, whilst LRO orbited above and observed the impacts. The debris and gases thrown up from the lunar surface were closely studied by LCROSS as it too descended to the surface. The missions found evidence that the lunar soil within these shadowy craters is rich in useful materials. The Moon is chemically active and has a water cycle. Scientists also confirmed the water was in the form of mostly pure ice crystals, which had not seen sunlight for billions of years. LRO has continued to operate in polar orbit, making observations of the South Pole, and with repeated flyovers, it has drawn up a detailed map of neutron densities in the region, revealing where hydrogen and thus water can be found within the lunar soil. The importance of this discovery cannot be overestimated. Having this resource in situ means independence from the cost and effort of bringing water from Earth to the Moon. It can be used for creating rocket fuel, oxygen to breathe, water to consume and to irrigate crops, and used in other processes to manufacture building materials from the lunar soil. Launched in 2007, NASA's 5 Themis spacecraft have now successfully completed their 2-year mission to determine the cause of geomagnetic substorms. Because they are continuing to work perfectly, NASA redirected the outermost 2 spacecraft to the Moon. This new mission was called Artemis, and they studied the magnetospheric environment near the Moon. They also observed the effects of surface electric fields and ions from the solar winds on the lunar surface, and determined the internal structure of the Moon from variations in its magnetic field.
Well, in a nutshell, what we're finding is that the polar craters are very unusual electrical environments. Well, the solar wind is actually a relatively tenuous gas that's emitted from the sun, but it's not a neutral gas like the gas in this room. It's actually a gas that's really, for the most part, free ions and free electrons. So as you pass by, for example, a polar crater, the electrons will actually fill into the crater ahead of the ions. Now, as it turns out, as it does that, you create an electric field. It's called an ambipolar electric field, and that electric field then drives in the ions.
These hidden troves of water ice and other volatiles in the polar craters may be protected by a dangerous electric charge of hundreds of volts.